Ready to go?
Yes.
Clock is ticking.
Okay. So good afternoon, ladies and gentlemen. Thank you for coming to our presentation. We are the autonomous UAV multicopter. We are building this to compete in the AU-BSI Seafarer competition. My name is Alejandro Diaz, and I'm here with Luis Ramos and Daniel Reyes. So, introduction to our project. We were tasked to build a platform to compete in the competition. The way that we split up the responsibilities, Luis Ramos was in charge of the system integration. Daniel Reyes was structural design, and I was tasked with competition tasks. So, introduction to the competition. The main focus of the competition is to come up with a platform to compete. We have to unmanned liftoff, take flight, and land. One of the metrics is target acquisition. On the top, you see the symbol. We're supposed to identify the shape, the color, the alphanumeric, the color of the alphanumeric, and the cardinal direction of the object. One other thing is we're supposed to have wireless communication to our base station in order to communicate the information back, and all within a minimum of 20 minutes. So for our senior design goals, what we set out to do was to increase the flight time. We're supposed to take the flaws of our initial design and try to improve it. So to increase the flight time, we are trying to reduce the weight, increase the stability of the system, increase the vibration dampening, special consideration for the component selection, as well as do efficiency tests and test out the autonomous flight. For the competition, we have to incorporate waypoint navigation, make sure that it completes the tasks in less than 40 minutes, and make sure that it's capable of in-flight retasking and target acquisition.
So I'm going to briefly go over why we decided to do a multi-rotor platform. Initially, we were advised to do a fixed-wing airplane and buy a fixed-wing airplane and then try to get it to fly and focus all our efforts on the competition, where we thought that wouldn't be adequate enough for senior design. We would just come here, show you something that we bought, and that would be it. So we decided to scratch that idea. Then we decided maybe do a helicopter, but financially we couldn't do it. Startup costs were just too much for us, and the manufacturing timeline, we just didn't have enough time to do it. So we decided to do a multi-rotor. Now the multi-rotor does have deficiencies and cons. It has different flight mechanics than usual, and the flight time. The flight time is the main deficiency of a quadcopter. So that was our main objective, to increase the flight time of our platform. So just a little quick introduction on the flight mechanics. We have 4 rotors, and 2 of them opposite each other spin clockwise, the other 2 will spin counterclockwise. That'll give you a torque cancellation in the center of 0. In order to roll and pitch, for example, to roll and pitch, 2 motors adjacent from each other, like let's say 1 and 2, will spin faster than 4 and 3, while 4 and 3 will reduce their speed in order to keep the same thrust and allow you to pitch and roll. In order to yaw, rotors across from each other, like 1 and 3 or 2 and 4, will spin faster in order to increase your torque, so you spin. Your takeoff thrust has to be greater than your payload, and your loitering thrust has to be equal to your payload. So we designed a prototype based on the component selection. The cost of the total frame, surprisingly, was just $25. Home Depot, aluminum rods, and a local architectural store gave us the acrylic for $25. We manufactured this thanks to the mechatronics lab and the architecture facility on the main campus. The initial flight cost, though, while we did pay $25 for the frame, the initial flight was $784 with all the components as you see here. And this is what our prototype looks like, and unfortunately we couldn't bring it today because of a little mishap. This was us flying it. There's no sound, but whoops. Oh, yeah, there you go. And obviously we're not too happy with that, but it's what we've been through this whole year.
So what actually happened there?
We'll go over that. We'll go over that right now.
Let them finish and we'll go over that.
So for our prototype testing, we had a lot to do. For senior, we wanted to focus on increasing the flight time, make sure we have enough, and also dealing with power distribution and efficiency, again, for flight time. But we also had tests we wanted to do for the competition, such as autonomous navigation, and telemetry communication. So this is one of our flight time setups. For this, we actually wanted to tether the plane, the aircraft, so it wouldn't move from its position. So we would focus just on seeing how much it could fly in the air. So you can see we tethered it with ropes to the ground. And this was one of our prototype flight tests. Next. Another test we did was autonomous navigation. So for this one, we would take off to a height of 50 meters, loiter for I think 500 milliseconds, and then come down to its launch position, all autonomously, just to make sure the GPS and all of the sensors and stuff were working. So this is a fully autonomous flight that you just saw there. Another test we did was stability. So we wanted to make sure that the thing was stable and it would be as efficient as it could. So apart from using accelerometers and all that stuff that's on board, we wanted a visual aspect, and this is a cool trick we did, just putting the camera under to see how stable it was, whether it was twitching or not, and seeing what we could do to make it better. Another thing we did was the testing of our power and efficiency. So we did a lot of motor and propeller combinations to see what we could do to make it more efficient and fly for the longest time we could. We did a lot of trade-offs between size, pitch of different propellers, as you see in the next slide. This is our jig assembly that we use. So this we use to measure how much thrust and how much current was being applied to each motor, and then we did different combinations of propellers. So here are the different propellers we used. You can see them here. This one I think is the Turnigy, and this one was the APC. So we applied different amps to each one and measured the amount of thrust we got versus how much power it was drawing. And this is a graph of thrust versus current that we got for those are the 5 different propellers that we used. The carbon fiber ones got us the best thrust, but this is not really useful for us because we have more than enough thrust with these motors. These were very expensive and very, very efficient motors. So what we wanted to do was do an efficiency test. So to do efficiency, we got how much grams of thrust per watt each propeller was drawing. And as you can see from this, the best one is the carbon fiber 15x4. And no matter what current you applied, it had the best efficiency, and those are the ones that are on the plane right now.
So, as for the imaging system, the approach for the software was to incorporate computer vision into the project. However, due to our time constraint, we decided to go with a man-in-the-loop system. As you can see on the laptop, you can actually see the screen. The person is supposed to be able to see the video stream and identify the objects. Unfortunately, there's a lot of electronics in here, so it's messing up the wireless communication. And because we have low light, it's messing with the sensor. But because we're going to be in an outdoor setting, much brighter, you do get a better picture. As for the hardware, we decided to go with a 5.8 gigahertz video system so that it's operating on a different spectrum than the rest of the electronics. The system that we have currently can go up to a 2-kilometer range as long as it has a line of sight to the base station. And for the camera, we're using a Turnigy micro video camera with a 3.6 millimeter lens. The electronics on this is actually separate from the motor electronics to keep from the motor interfering with the battery delivery to the electronics.
So after designing the prototype, we obviously wanted to build a final design and see improvements. And the one thing that we made a big improvement on was the body. In the prototype, it was aluminum bars with acrylic. We changed the entire body to carbon fiber. The one thing that's not carbon fiber is these custom clamps that we designed for vibration dampening. And we used 2 batteries instead of 1 for the final design. The cost of the final design frame was $200, completely different from $25, but you see those benefits in your decrease in weight by 56%, your increase in strength by more than 200%, and your reduced vibrations by half. We did all of this thanks to Mr. Richard Zigarelli in the FIU machine shop and in the Discovery Lab on the main campus in the computer science building. This is just the vibration dampening graphs. This is the prototype on the top and the final design on the bottom. As you can see, it goes by a factor of 2. It reduces by both X and Y and also in the Z by about a factor of 2.
So another thing we wanted to do for competition was communications with the judges. So in competition, the judges are going to have what they call an SRIC station, which basically comprises of a laptop computer, a router, and connected to a directional antenna, which beams up a 30-degree signal. And basically what they want you to do is communicate through the aircraft, through Wi-Fi, and collect a file that's on the computer and read the text that's on the file. So to test this, we built an exact replica of what the judges will have. So as you can see, Windows 7 computer with the Linksys router and this exact same antenna. And we did this to be absolutely sure that we could connect and we could do the communication that they require of us. And then on our side, we have what's called a GCS, a ground control station. We have a similar computer and a similar router, but a much better antenna that we purchased. It's a 24 dBi omnidirectional, and this is what we use to test the connection from both. So to test the range, we basically set apart these two antennas as far as we could until we lost connection. And we found a total of 1,200 feet was the distance where we didn't have a reliable connection between the two antennas. So now what you do is you introduce the aircraft, which has this little white thing, I don't know if you can see it, is a wireless repeater. And what it does is it takes a signal from the SRIC and it broadcasts it at a longer distance. And using this, we tested it to have a range of about 3,000 feet with the wireless bridge in between. And this was more than enough range we needed because the competition grounds has a radius of about half a mile. So no matter how far you are from the central station, you're going to have enough range to communicate with them. And this is basically the communication line that you would use to connect to them. So flight time. As we said, this is one of our biggest issues. And this is our first prototype flight time video that we did. We wanted to see how long we could stay in the air. So obviously we couldn't show you the whole flight time video, so we had to cut it. You'll see it as it cuts. We do have the full video, the full time that it flew in the air. But for this, again, we use the same tethering system to make sure it stays in one place. And on our prototype, with one charge of battery, we were able to get around 25 minutes of flight time, which was really great for us because the competition, they require you to be within 20 to 40, and the closer you are to 20, the more points you get. But this wasn't a good test because, I mean, obviously in competition you're going to be flying, you're not going to be hovering in one place, so that's going to be a lot less. So with the new model, we decided to do the same test with two batteries, with all the vibration dampening and all the weight reductions, and we did the exact same test with our model. And we didn't expect a 100% increase, but we did expect a pretty large increase because of the two batteries, because of all of our work that we did on the model, and we were actually able to get around 40 minutes or more on just two battery charges with our model, which we think is more than enough time, and we were really happy with the amount of time we were able to fly this with just two charges.
So in conclusion, stable flight operation, we were able to achieve that. We were able to successfully test the SRIC system for wireless communication. Video target acquisition capabilities, we can see that from the laptop screen. And vibration and weight reduction from the previous examples. And a 43-minute flight time. And we would like to take this time to acknowledge the following people who helped us with this project. Mr. Richard Zingarelli for manufacturing, the architecture department for manufacturing our plates, the mechanical department and the mechatronics laboratory, especially Maria in the office for helping us, Professor Tansel for mentorship and funding, and Dr. Kim from the Discovery Lab. Thank you.
All right. Well, first question, what caused the crash?
That crash, that was an autonomous flight, so we were testing takeoff and landings. And what we found is that the board that we use has a barometer, which uses to measure altitude through air pressure. And what happens if you don't cover that barometer and some wind comes along and blows over it, it's going to change what it thinks the air pressure is there. So what happened there, we looked at the logs. The plane thought it was much lower than what it actually was and decided to take off and go to a height that it was supposed to be at. So just things like that made us realize that we needed to, better our design, cover our barometer, and we learned a lot from all our crashes. This wasn't our only crash. We had lots of crashes, but like I said, our frame for our prototype was $25, so we could replace it fairly easily. The only thing that broke really was the acrylic holding the body, which was like $8, I think. So, I mean, we crashed a number of times with that.
Lessons learned?
Yeah, a lot of lessons.
Yeah. All right. Any other questions? Well, hearing none, I guess we're crystal clear. Thanks so much.
Thank you.
All right, we're going to